Alright, the curve C is described by the equation ln y plus x squared y squared is equal to 9. Show that the tangents of the 2 points on C, where y is equal to 1, meet at the point 0, 37 on 19. So first things first, we want to find the 2 points where y is equal to 1. So we'll take y is equal to 1 and substitute it into our equation. So let's do that. We'll have y is equal to 1. So therefore, we have that, well, ln y, if we have log of 1 is always 0. So we can ignore that. Let's plug the 1 into the y squared. We'll get 1. So there's going to be 1x squared. And that's going to be equal then to 9. So that tells us that we have x is equal to plus or minus the square root of 9, which is 3. Happy days. So we can think about the coordinates we get from that. They're going to be positive 3 and 1. And then also negative 3 and 1. Happy days. So let's move on then. And now we'll try and find the differential. So dy dx. We want to take our entire equation C and differentiate it with respect to x. So we can see here, like, some of the terms don't have x in them. Some have x and y, and some have just a constant. The constant's easiest, just going to go to 0 as normal. The bits where it's like a log y then. So we are differentiating with respect to x. What we need to do is use the chain rule. And we're going to change our d dx into a d dy and a dy dx. So you can imagine as a fraction, these cancel off. Doesn't quite work like that, but it's a similar idea. And then what we're going to have is still a ln y in here. So we end up differentiating the ln y with respect to y and just multiplying by a dy dx. So in implicit differentiation, whenever we have a term with just the wrong variable, so like here we're having d dx, but this has a y, we effectively differentiate with respect to the variable itself and multiply by the differential between the two. So with the wrong one and with the right one. So this then, the differential of ln y is going to be 1 over y. So this is 1 over y dy dx. Beautiful. When we have a term that has both, so the right variable and the wrong variable, the x and the y in this case, we need to use the product rule. So our d dx of x squared y squared, we can think about it as being equal to x squared d dx of y squared plus y squared d dx of x squared. So this term then is very similar now to the bit above. We're going to use the chain rule again, and we can think of like this d dx is going to become the same step as up here. It's going to become a d dy and a dy dx. So we get 2y from this, so we have 2y x squared dy dx. So 2y x squared dy dx. Beautiful. Over here then, for this second term, it's x squared and it's d dx. So that's just normal differentiation. So we get 2x. So altogether, this is 2x y squared. I'm just going to rub these bits out and write them back in alphabetical order. So we have x squared y. Doesn't make any difference, but can just be a little bit easier if we think about now, like they may end up being the same term at some point. So just have them alphabetical order means that we always know. It's a little bit easier to check whether they're the same. Right then, next step. We've differentiated x squared y squared. We've differentiated the log of y. So we've done both the left-hand side. The right is just a constant. It's going to go to 0. So we want to rebuild our equation, all differentiated. So effectively, we have this bit plus these two bits here. So that gives us 1 over y dy dx plus 2 x squared y dy dx plus 2xy squared is equal to 0. And now we want to factorise our dy dx and make that the subject. So what do we have? Well, we have 1 on y plus 2x squared y, all lots of dy dx. At the same time then, I will subtract this 2xy squared to bring it to the other side. And now we'll divide by the bracket. So our dy dx is equal to minus 2xy squared divided by 1 on y plus 2x squared y. And now what I'll do, just to make it a little bit easier, we will get rid of this fraction in a fraction. We do that by multiplying top and bottom by y. So the top now is going to be 2xy cubed, and the bottom, well, the y cancels with that one to make a 1, and in the second term it makes the y into a y squared. So we have 2x squared y squared. Happy days. We can see by inspection now, and like the fact that our coordinates, we have the y value the same, and the x value is just the negative of itself. So this bottom with the fraction, the numbers are the same in magnitude. The only thing that changes is the sign. So when we square things, that eliminates that difference in sign. So our bottom, our denominator, is always the same for both of our coordinates. And the top, what we have here is odd powers of both of our things. The y doesn't change, so we're not really interested in y, but an odd power of x. So that preserves the difference in sign. So what we can see is each coordinate is going to have the same magnitude of dy dx, just a different sign. One will be positive, one will be negative. So let's label our coordinates and find these differentials. So we'll label that one A, this one B. Draw a line down here, plug everything in. So dy dx evaluated at A. So let's think about what the bottom will be, because that's going to be the same in both of them when we do it for B as well. Well, we have 1, nice and simple. We're going to add on 2 times something. Well, it's 2 times 3 squared, so that's 2 times 9, times y squared, so times 1. So we have 2 times 9, 18, plus 1, 19. So 19 on the bottom. Along the top then, we are going to have a minus 2 for A, times by a 3, times by y cubed. But y cubed is 1. Y is always 1. When you cube it, you get 1 as well. So that gives us minus 6 on the top. So with our ideas of the negative, what we can say is for B, that's just the negative of the value at A, which is then 6 on 19. Beautiful. So now we want to use these derivatives, well, these gradients, I suppose, at these points, and find the tangents at these points, and then actually see if they do meet at this location. So we want to use y, y minus y1 is equal to m, where m is going to be the gradients we found in the step before. X1 is x1, where x1, y1 represents the points. These should be a 1 in there. So x1, y1 are our 2 points. This would be x1, y1, x1, y1. So let's do this. Generally, you'll find the tangents, but in this, we're going to see we don't need to. We'll have a step before where they can cancel out, because we just want to find this coordinate. So we want to find the x and y, given both of these tangents exist at the same time. So we're going to have y minus 1 is equal to m, which is minus 6 on 19, doing it for A first. And then x minus 3 for x1. Similarly then for B, what we have is y minus 1 again, and then it's going to be 6 on 19, so no negative. And again, it's now going to be x plus 3, because we have minus minus, which makes a plus. So altogether then, we can see we want simultaneous for these two. The left-hand side is the same, so we can just equate the two right-hand sides. So what we're going to get then is minus 6 on 19, x minus 3, is equal to 6 on 19, x plus 3. So we can cancel off the fractions, the 6 and the 19 at the start, and expand our bracket on the left. So we get 3 minus x is equal to x plus 3. Our 3's will cancel. And what we basically are left with is that x has got to be 0. We're told that 2x is equal to 0. So that tells us that x is equal to 0 as well. Beautiful. Now let's take this value. That is our x from the coordinates here, that show that. And we'll plug it back into either equation above and try and find the y coordinate. So subbing that in then, let's just draw a quick line. We'll have y minus 1 is equal to, we'll use the second equation simply because of the positive 3. So when we put the 0 in here, this whole bracket is positive. And here we have 2 negatives, here we have 2 positives. Bit easier to deal with the positive numbers. So we have 6 on 19 times by the 3, which is equal to 18 on 19. And when we add the 1 over, well, the 1 is 19 on 19. So 19 on plus 18 gives us the 37. So that is the 37 on the 19. So beautiful. We've shown that the two tangents do intersect at this point here. Happy days. Thanks very much.